General Electric realized $12 billion in savings over a 5-year period. This massive financial impact was the direct result of rigorous quantitative forecasting, a methodology that moved the organization beyond the subjective gut feelings typical of traditional management. I'm Alex, a Master Black Belt representing Six Sigma Development Solutions, Inc. In this video, we are breaking down the exact socio-technical framework required to predict project success before you commit your first dollar of capital. This framework governs both the initial planning phase and the real-time tracking of active project execution. Consistent project success is a measurable mathematical output. It is the result of deliberate process engineering rather than a series of fortunate accidents. As this map of the Lean and Six Sigma toolkits shows, project forecasting requires the strict mathematical alignment of scope, schedule, and cost. At its foundation is the transfer function, y equals f of x. In this equation, your output, the predictable return on investment, is the direct result of your specific project inputs. This function dictates that you cannot guarantee a high-quality output without first identifying and controlling the critical input variables. The primary obstacle to this mathematical clarity is the planning fallacy. This is the psychological tendency to underestimate time, costs, and risks by focusing on best-case scenarios. During actual execution, this manifests as catastrophic schedule overruns and a bloated cost of poor quality. Defeating this optimism bias requires an organization to replace subjective human estimates with rigid mathematical governance. Accurate forecasting begins during the project selection phase, long before a team begins work. This requires top management commitment to ensure that resources are formally dedicated to the forecasting and planning process. Every selected project must mathematically align with the voice of the customer, ensuring the effort addresses a documented business need. To eliminate individual bias during planning, we use the Delphi method. This process utilizes a network of anonymous experts who submit independent forecasts to a central facilitator. By iterating this feedback until the variability between expert responses reaches a satisfactory level, the organization arrives at a stable, group-derived consensus. Another critical input control is analogous estimating. This technique sets a realistic baseline by utilizing historical data and performance metrics from similar projects completed in the past. Controlling these initial X variables is the mathematical foundation of this framework, as the stability of the Y output depends entirely on the precision of these starting inputs. Once the project is active, we use Earned Value Management, or EVM, as the operational engine to track execution in real time. EVM integrates 3 core metrics, shown here as interconnected gauges. The first is planned value, the authorized budget assigned to the work you scheduled to perform. The second is earned value, which represents the budget value of the work you have actually completed. Third is actual cost, the financial expenditure for completed work. Dividing earned value by actual cost gives the cost performance index. A gauge in the red zone means overspending. Dividing earned value by planned value gives the schedule performance indexed. A lagging gauge means delay. The target for both indexes is 1.0. Any value below 1.0 indicates the project is losing time or money relative to the plan. While standard EVM is excellent for tracking performance at a single point in time, these static metrics lack the statistical power required to predict future outcomes. To achieve true predictability, we must integrate EVM metrics with statistical process control, or SPC. By plotting CPI and SPI data points chronologically on a control chart, we can observe the true statistical behavior of the project over time. This chart establishes the upper and lower control limits, parallel boundaries that define the range of expected performance. These limits allow managers to identify common cause variation, which represents the normal expected fluctuations in a healthy process. However, if a data point breaches the limit, the system flags a special cause variation, a systemic failure that demands immediate management intervention. This integration transforms a reactive reporting tool into a proactive mathematical early warning system. We can see this framework in action by looking at the results from St. Boniface Hospital. The hospital suffered from severe operating room delays because they relied on subjective human estimates to schedule surgery durations. They addressed the problem by implementing data-driven predictive modeling based on analogous estimating from past surgical cases. As this chart demonstrates, replacing subjective guesses with statistical modeling led to a 59% reduction in scheduling-induced overtime errors. This success contrasts sharply with the performance of PTXYZ construction during the development of several industrial plants. EVM analysis of these projects showed SPI and CPI values that consistently fell below the 1.0 threshold. Based on these metrics, the estimate at completion forecasted that the projects would require up to 110% of their original budget to reach the finish line. Calculating the estimate at completion early in the life cycle provides the necessary data to force a rebaseline and initiate critical risk mitigation. Even with advanced tools, 3 specific operational failures can undermine a forecasting model. The first is relying on ad hoc project selection based on gut feel, rather than using a KPI-driven project hopper to prioritize high-value initiatives. The second pitfall is poor data hygiene. Any predictive model is limited by the quality of the historical records it consumes. By identifying recurring patterns within historical datasets, AI-powered forecasting engines can reduce supply chain and project management errors by up to 50%. However, these models fail when fed garbage data. The precision of the output is strictly limited by the quality of the input. The third pitfall is the failure to act. If the cost performance index drops below 1.0 and management does not intervene, the data is wasted. A predictive framework is only as effective as the organizational discipline used to execute its findings. To ensure project predictability, first use analogous and Delphi estimating methods to strip away the optimism of the planning fallacy. Second, track CPI and SPI meticulously to monitor the real-world efficiency of your costs and schedule. Third, plot your performance indexes on control charts to identify systemic failures before they become irreversible. Every metric in this lifecycle must align with your strategic business objectives and the goals of top management. There is a significant difference between understanding these metrics in theory and architecting them into a live production environment. To bridge that gap, pursue formal certification. Visit Six Sigma Development Solutions, Inc. to master these tools and deploy them at a world-class level.